So, what happens when two waves encounter one another? We call this wave interference. In this video, we're going to look at what is wave interference, and we're going to explore how to sketch two waves in superposition. So interference occurs when two waves pass through the same space at the same time. So here I have a series of three diagrams. Here are two wave pulses. We have one wave pulse with an amplitude of 1 moving towards the right, and we have a second pulse with an amplitude of 2 moving to the left. Now when these two waves encounter one another, we call that encounter superposition, and what happens is the two waves add up together. So since this was 1 and this is 2, the superposition is 3. And what happens is the wave actually grows temporarily. The amplitude of this one is added to the amplitude of the second. But then what happens is the waves continue on their merry way, and the wave which had an amplitude of 2 continues going to the left, and the wave that had an amplitude of 1 continues to the right, as if nothing happened. So the two pulses add up when they meet, and we call that superposition. And since we're adding these two to construct that larger wave, we call the process constructive interference. So constructive interference occurs when the result is larger than the separate waves. So in contrast, destructive interference occurs when the result is smaller than the separate waves. So let's look at an example of destructive interference. So before we have a wave pulse moving towards the right, it has an amplitude of positive 2. And we have a wave pulse in the negative with an amplitude of negative 2 moving to the left. So these two encounter one another, and since they both have the same magnitude of an amplitude, but one's positive, one's negative, they will add up to 0. So I guess that would be the location of the superposition, but there's nothing there. So the waves momentarily disappear. But then, as soon as they move out of that superposition area, the waves reappear as if nothing happened. And so the wave which was positive 2 continues to the right, positive 2, and the wave which was negative 2 continues to the left at an amplitude of negative 2. So where can we use this idea? This is actually very useful, and we use it in those headphones for noise cancellation. So direct destructive interference principle is used in noise cancellation headphones, and essentially what happens, the headphones have electronics in them that are listening to the surrounding sound. So let's say that you're on an airplane and there's that continuous annoying hum of the jet engines. Well, the electronics pick up on that, and they reproduce that sound to some degree. There is a slight delay, but the sound, the production of that sound through the headphones is so nearly instantaneous that you get some degree of destructive interference. So as you're listening, as the sound from the jet engine is produced, the headphones are producing the opposite sound or the opposite amplitude, and that cancels out the jet engine noise. So let's look at, or let's explore the addition of waves, a technique that we use to analyze the interference of two wave patterns. Here I have two wave patterns. This one has an amplitude of positive 2, and this one has an amplitude of 1. So this is half the size. But we say that these waves are in phase with one another, and the reason for that is the crests of the waves all are in line with one another. So we say that the waves are in phase. And to determine what is the final wave pattern when these two are produced at the same time, what we do is we take that wave pattern and we subdivide it, and I have this subdivided with the green lines, and I've made markings with the blue dots to show what the value of the amplitude is at any given moment in time, and I've done that with both waves. So what we can do is we can take that first line and add up the position of the wave. So at this first green line we have a -2, and here we have a -1, which means when we add those two waves together, the result is going to be a -3, so I plot a dot right there. Now we get to the next dot, that's at 0, and this is at 0, so it looks like we're going to plot a dot right there, 0. This one is +2, and this was +1, so 2 + 1 is 3, so we position that there, and so on. We just continue. So in effect, because these two waves are in phase, what happens is this wave pattern is just simply added to that, and we have a larger, similar wave pattern. And this, of course, is going to be also in phase. And that will occur in the in-phase case. So let's look at an example where the waves are not in phase. So here I have a wave pattern that starts here at -1 and rises to a peak of +1, so the amplitude is 1. And here I have a wave which also has an amplitude of 1, but the difference is this one starts at -1 and this one starts at 0. So if we take all of the dots that I have here and add them all up, so along this first green line I have a -1 and a 0, that makes that a -1. And the dot in between the two green lines, here I have 0, +1, 0 plus +1 is +1, so then we plot a +1 there. Now when we get to the third dot, this is +1 and that's 0, so again we have a +1, and so you start seeing that the shape of our traditional sine wave starts to be altered. And this kind of looks like it's starting to become what's called a square wave, where the tops are flattened out. Okay, but there's a little bit of curving with the rest of it. Okay, so depending on how much the waves are shifted out of phase, we can result in various different patterns. So when the waves are not in phase, we exhibit both constructive interference and destructive interference, and it really depends on the size of the waves and how much they are shifted. Now, an interesting thing is, a fact is constructive interference, and I guess destructive interference goes in hand, is used in sending out multiple wave signals by riding a carrier wave. And we do this with radio, TV, and cell phones. What that means is that if we want to send multiple telecommunication waves, like multiple cell phone calls on a radio wave, what we can do is we can have one carrier wave at one particular frequency, and we can piggyback other signals on top of that carrier wave. And the way they do that is like my cell phone will produce this particular signal, and your cell phone will produce that particular signal, and it'll be sent on top of yet a third signal, the carrier signal, and it'll go from one point to the next, and when it gets to the final point in the system, there would be essentially a computer that would take that combined wave and break it up into individual waves. So your call and my call could be sent from point A to point B together from the East Coast to the West Coast, and then once it gets to the West Coast, it can then be broken up and sent to their respective phones. So this is a common thing that they do in telecommunications of all sorts.